What's up, guys? So we're back today with day 8 of Advent Code 2022. I recorded a video of me actually doing the solution, but after yesterday, which was a 2-hour video, today ran pretty long too, and I was trying to edit the video down and cut out all the time where I was just like staring, confused at the camera, and stuff like that. And I was just having to cut out so much stuff um, that I thought it might be more useful just to do a summary type of video of my solution. Because the puzzle today is actually not that confusing. Um, I think maybe I need to stop doing the puzzles first thing in the morning because I'm just not thinking at my best. So the general idea is that we have a grid of trees with heights, and in the first part, we're just trying to check if a tree is visible from the outside. So it is visible if all the trees between it and an edge are shorter than it. Now this, I emphasize an edge because in my first attempt that I spent 10, 20 minutes on, I was checking that it was visible from all edges. So it only has to be visible from one edge. And the solution I came up with is pretty ridiculous, as you can see here. But it takes the instructions very literally. So if we're at an edge, that's what I check first. Of course, so we read in the grid, pretty straightforward, and then we start looping over the grid. And as I was mentioning, the first thing we check is if we're at an edge, because they tell you at an edge, somewhere in here it says at an edge, it's 0. So if we're at an edge, or no, it is visible obviously if it's at an edge. So we can go ahead and count that immediately and just go on to the next part of our loop. As you'll notice, these ifs could of course be combined into one long if statement. We'll see my better solution in just a second. Okay, so now, again, very literal. I just say whether or not we have found a path to the edge, and then I start looping out from the current position. So I think of the current position as call or grid of ij, and we just go from, so this is looping over the rows 0 to I, so up to the ith row. We're checking if all of the trees in our path from that edge to our current tree are, if any, well, really what we're checking here, if any of them is greater than our height, we are going to break set found to false. So if we found a path through that, so if we didn't break, we didn't set found to false, then we can go ahead and continue and we can say, all right, it's visible. Otherwise, we're going to check I plus 1 to rows, so that's checking our current tree down to the end of the grid. And then we do the same thing for columns. You see a lot of copying and pasting. And this does work. If we run it, I get 1843, which is the correct answer. Okay, so with that, I can check out part 2. Check out master, and we can check out part 2. Now, you'll see here, the problem in part 2 is that now we need to actually count the viewing distance of each tree. So in this case, the viewing distance of the edges is 0, which I kind of got ahead of myself on earlier. And you can see that here. So the top part, of course, we're still loading the same grid. As usual, I destructively modified my part 1 code to get part 2 at first. So this all is the same. You'll see on the edges, I set scores ij to 0. Again, these ifs could be combined. And very much like the last one, I do this let mute count 0. This time, we actually have to go in the right order. We have to actually start at our tree and go out from it. So that's why I'm having to do 0 to I dot rev. Because we do just 0 to I in this case, we're going from this edge in, and our count's going to be wrong, because we need to actually count from here out this time. So as we go, we're incrementing our counter. And again, if we find a tree taller or equal to us, we can break, so we can stop counting. And then, nicely for us, the final score is the multiplication of all the counts. So we can just take scores ij times equal count. And this time, of course, instead of having tote, I built a another vector of vectors of the scores out here and set them all to 1 so that we can do this multiplication. Usually I default to setting it to 0, but of course you set it to 0, then you're going to have to set it the first time. You can't just do the times equals every case. So again, we just copy and paste that code for each of the other directions. So again, we start from I, go down, same thing, and then we do the columns. All the same thing. And then at the very end, we iterate over all those scores. So iterate over the rows, and then inside of that, we have to iterate over the columns of the rows. Take the max, and unwrap it. And you'll see that this one works as well, 180,000. Okay, so those are my terrible, naive solutions that got me the stars. Let's see what I've gotten up to after the video. So the first thing I did, well, we'll see the whole thing at once. So the first thing I did, of course, is bring back part 1 and part 2. And you'll see now, part 1 is much, much shorter because I'm using iterators. So as I kind of was mentioning when I was describing the original solution of part 1, what we're really looking for is that all of the trees in our path to the edge are smaller than our height, our current tree's height. So you can see that here, we're using this iterator all. The only trick is, what do you actually iterate over? So in that first case, where we were taking all of the entries from 0 up to I, we just take I, and we check that that we're taller than all of the trees. And you can see, as I was mentioning, that we can also combine these. So if we're on an edge, these are our 2 if we're on an edge things. And then before I talk about the other iterators, the last thing we can do is actually string all of these conditions together, cast it to a U size, and just add it straight to the total. So we don't even have an if statement anymore. We just turn this Boolean condition into a 1 or a 0, whether it's based on whether it's true or not. So this is much, much shorter than the original solution, and a lot cleaner too. Now to loop the other way on the rows, we just we can reverse our grid, and then we take rows minus I minus 1 entries from that side, and again we check that we're taller than all of them. It's a very, very similar idea for the columns, except that we iterate over grid I instead of grid itself. Now I did think about factoring these into their own functions, which I would almost definitely do if all 4 of them were the same. It didn't really feel worth it to make 2 of them. Like I could have 2 functions for this that could go in the all. I didn't really think that was worth it, but you could do that if you wanted. The other thing you can do is you can actually use iterators directly, like you can map over these, but and I did do a short solution like that, but I put it back in the for loops just because I like how it looks better. I don't like how nested it gets when you have like 2 maps inside of each other. Maybe there's an even better way, but I didn't find it. Of course, we can do something very similar for part 2. This stuff's mostly the same. We still have our for loops, and this time we do have to leave the if separate because we're setting scores to 0. But you can see, and this is pretty ugly, I think, but this is kind of the analog of what we have above. So in every case this time, we're taking the grid, iterating over it, taking I. In this case, again, we have to reverse because we need to go out from I to the edge. And we look for the position, the first position where we are shorter than another tree. So we can, if we find that position, we just use it directly. Otherwise, we have to unwrap I minus 1 because that means we got all the way to the edge, didn't find any trees taller than us, so we need to take that distance to the edge as our score. And we also have to add 1 to the score, and this minus 1. This is what I was getting at. Well, you guys didn't see the other video, but I mentioned in the other video, it's very easy to have off by 1 errors and this kind of thing. So this is, every time you see a 1 plus or a 1 minus, that's a potential off by 1 error. So we have to do this because we want a score of 1 if there's 1 tree, not a score of 0, which our position would give us. So that's why you get this plus 1. And this is minus 1 because, for example, in the sample, if our I is 2, we would get 0, 1, 2, and we don't find anything. Uh, oh, actually, maybe that one shouldn't. Maybe I should take this out. Probably should take the -1 and the +1 out. That might be better. Yeah. But no, I need this +1 in the case it succeeds, and then I need the -1 in the case it doesn't. So it's a little bit touchy, but it does work. So this is our first case from before, and then I could just multiply it directly with the other cases. So this is the second case from before, where we're looping from I out to the bottom edge. And you see this one actually doesn't have a +1, and I put a comment in here. I'm not really sure why this one isn't +1, because the columns even are +1, but it does work like this. So you can see that we were able to take both of these cases from really repetitive code. It's still somewhat repetitive. I mean, it's a lot of the same idea, but they are probably different enough that it's at least reasonable to have this code, and it's just shorter in general, and hopefully easier to reason about. So that's it for today. I guess I can run both of these. You'll see that still passes. We've got our assertions. Um, yeah, but that's it for today. Let me know if you guys enjoyed this kind of video more than the long and painful process of watching me actually do it. I do have that recording. If you really want to see it, I can upload that later as well. But anyway, thanks for watching. We did get our stars. Have a nice day.